introduce Jeremy Brown. He is coming to give the control seminar today from Johns Hopkins, where he's been since 2017. Before that, he was for 2.5 years a postdoc with Catherine Kuchenbecker at UPenn. And before that, he was here at Michigan. He, in fact, was a graduate of my lab and a regular attendee of this seminar series. So look forward to your talk, Jeremy. Thanks for coming.
All right, perfect. Thanks. And I guess this works. Yeah. Okay, cool. Thank you, Brent, for the introduction. It's great to be back at Michigan. I think I realized yesterday that this is actually my first in-person seminar since the pandemic. So it feels good to have my first seminar be sort of back at a place that I consider to be home. So today I'm going to be talking about work that I've been doing in my lab at Hopkins. Looking at haptic feedback and the utility of haptic feedback in various telerobotic applications. So what that really means, so the formal title is Understanding Utility of Haptic Feedback in Telerobotic Devices. Sort of what I've sort of reframed it as is sort of things that we've learned about the beauty of human sensory motor control across the biotic abiotic interface. And then, sort of beyond that, the other thing I want to do is talk about, what I've been doing since I left U of M. I know there's a large, population of graduate students in this, in the audience. And so talk a little bit about maybe not necessarily my journey, but where my journey has been since leaving Michigan. But before starting that, I will talk about my journey at Michigan because I had the esteemed pleasure of riding on a Blue Bus yesterday, which was a lot of fun. I actually haven't done that since probably 2014. And I was surprised to see that all of the routes still exist. And I didn't even have to guess. I needed to get down to Rackham and I was like, I can take the commuter southbound. And I just sat outside in front of Pierpont and sure enough, it came and I got to Rackham and made my way to my hotel yesterday, which was a lot of fun. Before I go any further, I will sort of stop and acknowledge, all of the students in my lab that have contributed to the work that I have the pleasure of presenting to you today. I think it was Dan Kotajek, who is, not an unfamiliar name to many in this audience here, who told me when I was a postdoc at Penn that you go into the faculty career, the most important thing that you produce are the students that come out of your lab. And I think that's really true. Having now had my first 2 PhD students defend and land successful jobs, I feel like I'm now officially a faculty member. And so I just wanted to acknowledge all the work that I get the pleasure of talking about. So with that, I would sort of jump into the actual meat of the talk here. And I'll motivate it just by talking about upper limb volitional control, dexterous manipulation, right? Things, as you see here on the board, tasks that we do kind of in our daily experience, maybe for, activities of daily living, but also maybe for work and then also for pleasure, right? Most of the activities that we do revolve around this tight coupling between action and reaction, or motor control and sensory feedback. For, sort of the quick primer for, those that maybe haven't thought about, sort of closed loop sensory motor control in humans, right? We always think about it as starting with the brain, and we send these efferent commands out from the brain out to the motors in the periphery that cause the motors to contract, then muscles move, limbs move, and they interact with objects in the environment. Most of the time we interact with the world, we watch the objects around us, not always the case, right? You can stare at me, probably pick up your cup of coffee and drink it without actually having to look at your cup of coffee. But at the same time, every time we touch objects in the environment, there's a sensory pathway that starts at the periphery and moves back to the brain and sort of closes this loop for us, right? And we use this information to track task progress. If I pick up an object and I put it down on the table, I'm waiting for that confirmation signature of the object kind of making contact that I know I can let it go, right? We, sort of know once we feel the weight of the object that we've got it successful. We know we can feel signatures around stable grass. So I know that you probably already believe this, but work with me for a little bit on this. I'm going to show you how important sensory feedback actually is, and I'm going to use an example of sort of striking a match on a matchbox. This is a very, very old video out of the group of Roland Johansson, who's really a motor control neuroscientist. And what you're going to see is a participant try and light a match or strike a match on a matchbox after they've had their hands anesthetized. So all of the cutaneous afferents that sort of exist in the hands no longer really are sending signals up to the brain. And this participant is going to try and light the match. And that's what you'll see in this video here. Okay, two things to note from this video. One, performance was really bad. I mean, could you imagine somebody trying to light candles on your birthday cake, and this is what you see, right? That's like really depressing. The second thing, though, is that the participant was still able to do it, right? And that's because they still had vision. Vision wasn't included, and that shows just how visually dominant we happen to be. And I would argue that actually that's the reason most of our robotic interfaces, especially human robot interfaces, telerobotic interfaces, are able to work, is because we can be visually dominant and we can rely on visual information to sort of substitute for the lack of haptic information in most of these robotic interfaces. So sort of moving into telerobotics, how we get there. So we know we use our limbs to interact with objects in our daily environment, but there exists, environments where direct manipulation is sort of not desirable, either because, it's, sort of a remote environment that we can't physically manipulate in. The environment poses dangers or hazards to our body. It's on a different scale as our body, or we've sort of contrived limitations or access into the environment. There also exist situations where the body itself changes conformation. And there we're not able to do the sort of standard activity of daily living type manipulation that we think about with our intact or healthy limbs. In both of these situations, what we need is an interface that takes the action that we want to impart on the environment and basically carries it out for ourselves. This interface we sort of refer to as a teleoperator. The original teleoperators were invented in the 50s and 60s by a scientist by the name of Raymond Gertz. They were designed to sort of handle radioactive material behind lead glass plate. And this is an example of one of the earliest teleoperators. So what's really nice about these teleoperators is that they're purely mechanical, right? Just cables and linkages that connect what we call the leader side to the follower side of the device. And because of that, you get good one-to-one mapping sort of in the forward path, right? You move a centimeter on the leader up, and the robot, or I should say the follower moves a centimeter. Because of the inherent cable linkages, there's inherent force reflection, right? If you watch the video, there was a part where the manipulator hit the table. They don't show it, but I imagine that the operator controlling the other end felt that bump as well, right? It's just pure cables and linkages connecting the two sides. For various reasons, including just the inertia of adding, extra linkages and cables or the degrees of freedom, we've moved away from actual teleoperators, purely mechanical teleoperators in most senses, and now think about things with the advent of electromechanic actuation schemes as telerobots. And in my lab, and this started actually with work with Brent, we like to think of a prosthesis as a teleoperator. You're operating a distal robotic device from more of a proximal location on the body. Most telerobots, sort of work under the same principle. We've done a really great job of doing one-to-one mapping, sort of, what is the action you want to take on the environment? The robot carries that out on the environment for you. Because these are robots, they have a suite of sensors on them, and we can measure all of the interactions between the robot and the environment. But it's generally the case that information, especially the sensory information, doesn't get passed back to the operator. So you can't do this closed loop dexterous manipulation. And so what my lab and Brent's lab and other labs around, are focusing on is how can we add this haptic interface to these telerobotic applications in order to close that sensory motor loop. So I'm going to talk to you about 3 different types of applications that we've been working on in the lab. The first, upper limb prosthetics, I'll spend the most of my time on because that's work I actually started here as a grad student, and I've been continuing sort of in my own research lab. But I'll touch a little bit on the work that we've been doing in the robotic minimally invasive surgery space, as well as some work that we've been doing kind of in understanding, fundamentally haptic perception, how it works, and looking at perception through robotic interfaces. And so the work that I'm going to talk about in the upper limb prosthetic space is actually done by my former PhD student and postdoc, Dr. Nehan Thomas. So if you were to have an amputation of the upper extremity today, there's sort of 2 types of prostheses that you would get. The first is a body-powered device. The second is a myoelectric device. The body-powered device, sort of post-Civil War era technologies, pretty straightforward. It's a cable, that connects to a shoulder harness, that pulls the actuation of the cable by flexing across the harness, basically causes the hand in most cases to either close or open, right? And it's usually sprung open or closed kind of when you're not actuating it, right? What's really nice about this is that you get control action from the body. Because of that, you have inherent haptic feedback because of the cable linkage. Think back to the Gertz style teleoperator. The problem though is that, for most of these devices, you have limited degrees of freedom. Generally speaking, you're only talking about a single degree of freedom for the amount of input actuation. As I mentioned before, these devices sort of operate like your standard Gertz style mechanical teleoperator. Good mapping in the forward path and good force reflection in the backwards path. Then we have, and so I should say, sort of to go back, actually one of the studies that I did as a grad student here was sort of proving that this force feedback or force reflection that you get in a body powered device actually has added utility. In order to do this, we basically built a body powered device that wasn't really body powered. It was actually, or I shouldn't say wasn't purely mechanical, it was electromechanical. And maybe this thing has a video, I think, that works. Yeah, so you can sort of see these linear actuators in the background basically pulling on the cable, one to pull on an exoskeleton, and the other to actually cause the prehensile to open and close. What that allowed us to do is basically turn on and off the haptic feedback. So we could still do good one-to-one mapping in the forward path to get the hand to open and close, but we basically turned off the actuator that provided force feedback. And we saw that there was a significant drop in performance now when you don't have this haptic information, even if you do have visual cues. So the other type of prosthesis is a myoelectric. Control action comes from the electrical activity of the muscle. You can get increased degrees of freedom. Things like commercially available iLim, Autobot hands, right, have articulated fingers, articulated wrists. You can do different types of grasp, things like that, but they don't actually have any haptic feedback. And so, again, thinking about a prosthesis as a telerobot, we've now started, we work in my lab to figure out, how can we add novel haptic interfaces in order to restore this haptic information. As a grad student here at Michigan, I spent a lot of my time looking at exoskeletons as one of the ways in which you could add haptic feedback to these prostheses. The idea here that we were thinking about was very much so motivated by a body-powered prosthesis that you could sort of, kind of couple action and reaction sort of about a joint to drive the myoelectric prosthesis. And so I walked out of, kind of finishing my PhD, sort of looking at, can we use these exoskeletons to sort of provide haptic feedback for a myoelectric device? Then I got to Hopkins, and with Neha, one of the first studies we sort of ran was we wanted to prove that these exoskeleton style devices really had added advantage and utility over something like a vibrotactile interface, which is sort of one of the standard approaches that folks in the haptics community use to provide haptic feedback. So we ran this study where we basically compared a prosthesis with vibration feedback to a prosthesis with what I call joint torque feedback, which is the exoskeleton, to a prosthesis without any feedback. What we did is we built a mock prosthesis that allows us to work with able-bodied participants. It uses the same sort of linear actuation scheme that I developed here as a grad student, coupling the grip force that we can measure from our prosthesis to both an exoskeleton and to a vibrating actuator now. So we can map this force information that we measure at the grip to a torque about the elbow joint and to a vibration on the arm somewhere. So the first step that we did, actually, in order to be able to make this an apples to apples comparison, is use this approach called cross-modal matching. It was something that was sort of taught to me by my colleague, Brandon Pitts, who was a PhD student here with Nadine Sauter in IOE, where if you want to be able to, sort of compare sensory stimuli, you need to actually equate them perceptually, right? So that I'm not necessarily doing better with stimulus A because I just happen to feel stimulus A stronger than I do stimulus B. And so what we ended up doing is coming up with this approach, basically, where we let users sort of feel the stimulus, the torque about the elbow and the vibration, and sort of adjust each so that they perceptually felt equivalent to each other. So one unit of torque now felt equivalent to 1 unit of vibration. And what we got are these interesting sort of user-derived functions that we then use to sort of do the mapping so that we were ensuring that we were giving equivalent stimuli in both cases. The task that we had participants do was this object identification task. So you had these 3 objects that you see in the red box there that were, they basically different in their stiffness. We had soft, medium, hard, and just different ratios of silicon, Ecoflex in this case. The task was to grab the object, squeeze it. We sort of occluded vision in this case, because I've already shown you vision is actually really good. You know, and vision can sometimes supplant for the haptic information. But we asked participants, you know, at any given time, we gave you 2 objects and we said, squeeze this one, squeeze this one, which one is stiffer? Kind of in a standard, what we call 2 alternative force choice psychophysics paradigm. Basically, what we found is that both feedback modalities, the vibration feedback, the joint torque feedback, did better than the case where you didn't have any haptic information at all. I mean, this result is not really novel. There have been other results that we, you know, that I did as a grad student to sort of kind of showed this. The interesting thing that we found is that there was actually really no difference between the 2 feedback modalities. People did just as good with the joint torque feedback as they did with the vibration feedback. And that was sort of eye-opening because I originally came into it with this hypothesis that this joint torque, you know, because it is, you're measuring a force and I'm mapping it as something that is very close to a force, which is a torque, it would be, you know, participants would perceive it better, would be able to intuitively make more sense of it and actually do the task better. It turns out that it's just a mapping. And if you sort of learn the mapping, and what we are now finding is that it doesn't matter. As long as you understand the mapping and you can make sense of the mapping, you can still use that information to do the task really well. We also think that that cross-modal matching paradigm that I showed you before sort of washed out any effect that we thought we would likely see, because now what we basically did is equate these 2 stimuli perceptually, right? So what this sort of allowed us to do is say, okay, well, let's just assume that they are maybe equivalent in terms of their utility for this simple task. And what my student Neha then decided to do is go on and, you know, using vibrotactile information for the rest of the studies where we got to get more interested in different control paradigms for prosthesis. And I'll start talking about that. But let me first, before I get to that, talk about another quick study that we did that was sort of based off some work that I started here at Michigan as well, where we said, okay, we know haptic feedback has utility. We've seen it, you know, it can allow you to do this stiffness discrimination task really well. But the question becomes sort of, we can show that it's better than the case where you don't have any haptic information or prosthesis. What happens if we compare it to our healthy intact limbs? Like, how good are we to, you know, what we call the gold standard? And what we wanted to look at was not only task performance, so how well do you identify, in this case, it'll be another stiffness discrimination experiment, but we also wanted to look at cognitive effort, right? So even if you're doing the task really well, if it takes a lot of mental effort to actually do it, does that actually mean, you know, is this the right solution, right? And so what we started doing, and this is in collaboration with my colleague Hassan Ayaz at Drexel University, is starting to think about this phenomena that we call neural efficiency. And the easiest way to think about it is, you know, if something is very neural efficient, you have very high task performance, very low cognitive effort. Right? If something has low neural efficiency, you have very low task performance, very high cognitive effort. And so we wanted to see, do these different control modalities with haptic feedback, without haptic feedback, how do they compare to the natural limb in terms of neural efficiency? And so what we did, sort of same basic experimental paradigm here, except in the top left, what you'll see is this little band across the participant's forehead here. It's a non-invasive imaging modality called functional near-infrared spectroscopy. What it basically does is, oh, look at that. It looks at the level of oxygenated, deoxygenated hemoglobin in the prefrontal cortex. And based on principles of neurovascular coupling, you can sort of make approximations of what someone's cognitive effort is at any given time. And so we started using this approach to now say, can we look at the performance of these different haptic feedback modalities? I will say that we were not, this wasn't the first time we thought of this idea. Actually, this is a study that we ran when I was a grad student at Michigan, where you can still see that same FNIR system there. Unfortunately, we never got a chance to analyze the brain imaging data there because of some complications in syncing data acquisition systems and stuff that I could probably talk about and lament about for too long. So we decided to sort of run this study again now and look at the brain imaging data. You also see there's an EEG system there. We sort of cleaned that up, didn't do EEG this time around. But basically the task was the same. Give the participant two objects, ask them which one is stiffer, they squeeze both of them, and they identify the stiffer of the two. What we found, as you can see sort of in this graph, is that performance actually differed depending on the object pairs that we gave. So performance was different if we did soft medium versus medium hard versus soft hard. So for the sake of argument, I'm going to just focus on soft medium because those were the two that were the closest in terms of their actual stiffness. We use sort of the standard EcoFlex mixtures. And so it's not like we had a linear rating between soft, medium, and hard. So soft and medium were actually really close together. But basically what you see is that the hand, which is highlighted, the intact healthy limb, which is highlighted in blue here, is perfect, right? Every time we said which of the two is stiffer, you could always identify which of the two was stiffer between the soft and the medium. When we asked participants to do the task without feedback in the prosthesis, which is the yellow polka dot there, it was basically a shot in the dark. Right? It's it's a 50-50 chance about, if you just guessed, you would get it right half of the time. And that's about what we found, right? The accuracy was right at around the guessing rate. But when you add the haptic feedback back in, sort of giving them this haptic information of their grip force now, you get a significant improvement in their task performance. Still not as great as the natural limb or the other gold standard, but significantly better than sort of the clinical standard. So that's task performance. What happens now in cognitive effort? What you're seeing here is a change in oxygenation. And what we're looking, so the FNIR sensor, just to dive in a little bit deeper, has a series of optodes around the forehead, looking both laterally and medially on both sides. And you're only looking at one optode. I believe this is left medial. And this is the one where we saw the most activities in terms of the brain. Just for the sake of arguments, I'm going to focus only on the soft medium block combination again, because that's where we sort of saw the biggest change in terms of task performance. But what you're looking at now is a delta. So we take a measure at the beginning of the task, and then we take another measure at the end of the task, and we compute the delta. How much did the oxygenation change over the course of the task? Basically what you see for the natural limb, blue, it's essentially zero, right? The task is actually relatively easy. You remember, again, task performance was at 100%, and it doesn't take much effort to reach that 100%. The prosthesis without haptic feedback had the largest delta, which means, again, remember that task performance was around guessing. So participants were actually guessing, and this delta kind of shows you that they were sort of trying really hard, but at the end of the day, still somewhat guessing. And when you add the haptic feedback in, you get a significant, let's say, increase or decrease in cognitive effort from the clinical standard prosthesis without haptic feedback. We're still significantly worse than the natural limb. It kind of makes sense, right? You've had a lot of experience with your natural limb. This is a new sort of control paradigm, new device, but that we get significant differences now in a matter of, let's say, a 30-minute experiment shows sort of the utility of the haptic information. And then we can compute this neural efficiency. And basically what we see is that overall, the intact limb, which we have the most experience with, has the highest neural efficiency. The prosthesis without haptic feedback has the worst neural efficiency. Remember, really bad task performance, really high cognitive effort. And the prosthesis with haptic information actually has neural efficiency that's sort of approaching what the natural limb does, definitely nowhere near there statistically, but at least trending in the right direction and significantly better than what we could do without the haptic information in the prosthesis. So sort of the closing story of this is that not only does haptic information or haptic feedback in a prosthesis lead to improved task performance, but it also leads to a decrease in cognitive effort, right? So you can do the task really well, and it takes less mental effort to do that well. So sort of shifting gears a little bit now into more of thinking about sort of interesting control schemes. My former student Neha got interested, and this is actually some work that she had pitched in her NSF GRFP proposal. It said, hey, when we look at volitional control, it's really not just that original kind of diagram that I showed you of control coming from the brain out to the periphery and from the periphery back to the brain. That's only half the story, right? That's more of our volitional control pathway. There's also this other control pathway that we refer to as our reflexive control pathway that actually starts with the stimulus at the periphery. And the stimulus at the periphery then generates, heads to the spinal column and then generates an appropriate motor response, right? That actually doesn't go immediately to the brain. The obvious obvious sort of example is you touch a hot stove and your hand jerks away from the stove before your hand before you cognitively realize my hand is now burned. Right? There's this reflexive motor pathway that happens that is a lot faster than the cognitive pathway. And so we started asking, can we combine this sort of volitional control pathway with this reflexive control pathway on the prosthesis? This is some work she did as a Fulbright fellow when she was at Max Planck in Stuttgart, Germany, working with Dr. Catherine Kuchenbecker, where she designed this prosthesis that had two different types of sensors on it. You can think of it as a 2-digit prehensor, so sort of like this. One sensor was a little pressure sensor down here that basically told you how hard you're squeezing. The other sensor was a big electrode that ran over the length of the finger. And every time you made contact with it, you basically closed the circuit. And so we could get information out about contact, where you made contact on the surface of this finger. So we had a contact location sensor, and then we had this pressure sensor. And so what we said is, can we hook these two up in this sort of volitional and reflexive control pathways? The task that we had participants do was this sort of what's called a reach to pick and place task. So I don't have a good example here, but it's like me picking the mic up from this bin, right, and putting the mic down in that bin, right, without actually breaking eye contact with you, right? And that's what we had participants do. Stare at a target on the wall, reach, grab an object, pick it up, move it to the other bin, and put it down. Something that individuals with healthy sort of sensory motor control can actually do relatively well, because you can rely on that sensory information again to sort of guide you through the task. We were wondering now, can we do this with this sort of novel volitional reflexive control pathway? And so what I should talk about, let me take a minute and explain how it works. The volitional control pathway, which I'll show kind of on the next slide, we take the contact location information and we map it to two different types of sensors. The first is a vibrotactile actuator, which I've shown you before. And then the grip force or pressure sensor, we sort of couple together, and you can see in this column right here, these are the waveforms that we sent to the vibrotactile actuator. So we're modulating both the amplitude and the frequency in order to be able to give these two pieces of information: where you're making contact along the length of the finger and how hard are you actually squeezing. We also had this other device called the bellow band, which is a pneumatic actuator that has bladders. I'll show you in a second how it works. But you can imagine it as a band that you wear around your arm. It has little bladders that you can pneumatically inflate and deflate. And so both of these sort of close the loop around both contact and then grip force. So this is our volitional information that we're giving, or the haptic feedback that we're giving for volitional control. At the same time, we had two different autonomous controllers running on the prosthesis. The first was an anti-slip controller. So if the object started to slip, it would squeeze a little bit tighter. The second is what we call an overgrasp controller. And the way that basically works is if I have, the object is cylindrical, if I squeeze too hard, right, it pops out. And so the overgrasp controller sort of modulated the EMG signal to make sure you weren't grasping too tight, but tight enough to hold it, but not so tight that it sort of forced it out or forced it into an unstable position. This is an example of what the bellow band looks like. You can sort of see the bellows actuating here as you're moving, as she's sort of moving and making contact along the length of the digit. So we sort of hypothesized that this bellow band was actually going to do better. Again, probably in retrospect, anytime we sort of bet against vibration, we sort of have been losing. But that the bellow band was going to do better than vibration because it was sort of a modality matched. If I touched you here, I inflated this bellow. If I touched you here, I inflated this bellow. And so we thought it would be spatially a lot easier to sort of understand this information now, as opposed to sort of encoding it in this like weird waveform of vibration where we're modulating both amplitude and frequency. We thought it would just be easy to interpret. The task, as I mentioned, reach to pick and place. We sort of broke the task into 3 phases. You had to pick the object up, you had to transfer the object, and then you had to put the object down in the other bin. Remind you that you had to do it without looking at the task. So we had a target on the wall that you had to stare at, and we had participants wear eye tracking glasses to sort of look at, sort of making sure that they were following or compliant with instructions. This is a video of what it looks like. You can actually see where they're sort of looking at where their gaze is at all times as they pick the object up and put it down. The little pulleys wire system here is just sort of to do sort of weight compensation of the prosthesis, so it's not so heavy to do the task. So we sort of support the weight at about what the weight of an actual prosthesis is. So it sort of feels more like a real prosthesis. As you can see here, we're working mainly with able-bodied non-amputee participants. And so what did we find? What you'll see, let me describe the graph first. This is looking at sort of the probability of successfully lifting an object up. So grabbing it, picking it up out of the first bin. On the x-axis, what you're looking at is sort of in our statistical model, we had to account for the fact that even though we told participants to stare at the target, they didn't always stare at the target. And so what we sort of model is how often do they look away? We don't know if they're necessarily looking at the task materials. All we can sort of say is, are they looking away from the thing that we kind of told them to look at? And so when we account for that, in our model, you can see just over, you can just see visually, the more you looked away, the more likely you were to be successful in the task. But overall, when you sort of account for this like looking away behavior, what we found is that the autonomous reflexive controller and this sort of reflexive plus volitional or shared control actually led to better likelihood that you would successfully pick the object up out of the bin. Then transferring it, what we found actually was that only the case where you have the haptic feedback and the autonomous controller together led to a successful transfer. The reason that we think that is because picking the object up sort of is one challenging feat. But the minute that you move it, if the grasp was unstable, right, the sheer fact of translating it started to make it come loose and it would fall out. So what we really start to see is that it's really the reflex and the combination of the autonomous and the haptic feedback that allow you to stably transfer the object and keep it in your grasp, more so than just the reflexive controller by itself. And we think that's because the haptic information, remember we use that contact location sensor. Over time, participants got really good at figuring out where you actually needed to grasp the object in order to secure a stable grasp to begin with. Whereas in the reflex controller, you don't have that information to sort of secure a stable grasp. And so oftentimes that would get picked up in a grasp that wasn't stable. And when they tried to transfer it, right, the object just like fell out. Then, of course, when we look at, how likely were they to put the object down, there are no differences across conditions. And that's really because picking it up and transferring it were the hardest steps in the task. Putting it down was somewhat trivial at that point. And so we don't see any differences there. So what we started to do now with this is sort of say, there's something here to sort of combining these autonomous controllers with more haptic feedback, volitional control, and it sort of leads to better performance than just the reflexive or the autonomous control themselves. Because right now, when you look clinically, there are a few hands out there like the Autobot speed hand that have these reflexive controllers on them, that all they do is just sort of wait and see if the object is slipping and they grip tighter. And so we're sort of making an argument that you just can't have a reflexive controller. You need to have both this autonomy and this haptic information in order to do robust volitional control. Where we've gone with this now is starting to look at tasks that require very fine-tuned grasping forces. And so we have this object here that we call or we refer to as our instrumented object. What you'll notice about it is it has a container at the bottom where we can take, it's a little drawer, we can put weight down inside of it so we can change the weight of the object. But the participants, just visually, you don't know how much weight is inside. And it has this little door right here, or this side that basically is held together by a magnet. And so if you overcome the magnetic force, the door breaks and the object collapses. So what we've created is sort of a brittle object where there's a sweet spot where if you don't grab it hard enough, you aren't able to successfully pick it up. But if you grab it too hard, it actually breaks. This is an example of it breaking. And I don't know how my sound is going to connect, but let's see. So you can sort of hear it here every time it breaks. Again, as with most things, this idea is not novel. This is an example of so we had a little bit of a different autonomous controller in this case. What we relied on here was more of an imitation style autonomous controller. So what would happen is if you went in and you picked the object up and you successfully held it, the autonomous controller just remembered what was the grip force that allowed you to be successful in picking the object up, so that the next time you put it down and went to grab it, the autonomous controller kicked in and actually did all of the grasping for you. And so when I play this video, you can pay attention to the little orange box there. The signals are not really bright in this on this screen, but you'll see the little line jump up. It actually shows when the autonomous controller kicks in. So this first grasp is sort of manual. The person is using haptic feedback they're getting vibration to sort of successfully pick it up. The next time you can sort of see this blue light goes on and let you know that autonomy is kicked in. And so the next time they go in, it's not them that's volitionally controlling it, it's the autonomous controller that's going in and sort of determining the grip force to actually pick it up successfully. I will just highlight here, as I said, this task is not novel. This is another variant of a task that we tried as a grad student, where we had another version of this instrumented object here. We sort of have been going back to some of these basic principles experiments because there's a lot of interesting questions that we still haven't answered in this space. Sort of to get to the data of this, what did we find? So we ran a study with able-bodied participants where we had this controller, the haptic feedback volitional control plus this autonomous controller that does this more mimicry style control to actually do the task the second time around. What we found, and we call this sort of a haptic share control, this haptic share control did better than both just haptic feedback by itself, so just getting haptic information and using that to modulate grip force, and did better than the case where you don't have any haptic information in terms of task performance. In terms of mental effort or cognitive effort, which we measured again in this task, only the haptic share control led to a significant decrease in cognitive effort. And so when we look at the overall neural efficiency, this haptic shared control now, where we combine the autonomy and the volitional control, actually leads to more neurally efficient control strategies. So what we're seeing here is that the same behavior that we saw with the object discrimination task, now we're starting to see this in these more complex dexterous manipulation tasks now, where haptic share control, combining these, the haptic information with the volitional information, or with the autonomous information, leads to, better, more efficient, especially neurally control strategies. Where we started to go with this work, we over the summer have started now testing with actual amputee participants. So what you'll see in this first video is a participant using her standard clinically prescribed prosthesis. I think this is the iLimb hand. And what you will hear is this participant trying to grip the object and is somewhat unsuccessful in every attempt. And the clicking sort of means that the object is crushed. You broke the object, so you can't actually pick it up. And then what we then did is had this participant wear our sort of experimental prosthesis, where we had this volitional and autonomous controller going at the same time, and had to do it again. Now, of course, because I get to sort of pick the videos that I show, I'm going to show you the one that was the most successful. But by and large, this was sort of what we found is that the majority of the time that she tried to pick it up with this new sort of prosthesis scheme, she was a lot more successful, and that's what you'll see here. Still had, as you can see, there were still times when you weren't successful. But basically, we would go 2, 3, 4 times in a row where she could actually successfully pick it up and put it down. And again, sort of remind you, with her clinical prosthesis, she never got to the point where she was actually able to pick it up. Okay. One of the other things that we've been doing in the prosthesis space is sort of looking at overall, kind of the design of prostheses themselves. What you see on the left is the bionic hand. What you see on the right is an illustration of a natural limb. While, kind of form-wise, they look exactly the same. You've got a thumb and you've got 4 different fingers. In terms of their actuation schemes, they're inherently different, right? The bionic has motors that are sort of embedded down here that sort of allow the hand to do flexion and extension. And we know that our actual limbs actually rely on a series of tendons, both agonist and antagonist tendons, that allow us to be able to do articulation. What's really nice about this agonist-antagonist structure is that not only can I actually control the position of the limb, but if I co-contract both sides, what I actually end up controlling is the endpoint impedance or stiffness of the limb. And so we modulate our endpoint impedance or stiffness of our limbs kind of all the time in different tasks that we perform. And we begin to ask questions: can we build prosthetic limbs to sort of have this agonist-antagonist structure inherently in them? So I had a master student at the time sort of put together the first prototype of this. We refer to this as our anthropomorphically driven prosthesis. I'll show you a video in a sec, but I'll try to walk you through it. There are two motors here on the prosthetic socket, one here and one up top, and there are cables or tendons that run all the way to the hand here. On the top and bottom side of the hand, we have a series of tendons that sort of go to the fingertips. We don't do individual actuation, but we can do kind of full hand actuation. If we pull on this set of tendons, we can cause flexion of the hand. If we pull on this set of tendons, we can call extension of the hand. If we pull on both tendons now, what happens is we make the hand extremely rigid. And we also sort of tried this interesting haptic feedback scheme that hasn't really worked out. Largely because of the socket design. And so I've had a student this summer actually work on these sockets are formed at an OMP clinic, a prosthesis clinic, using thermoplastics. What we've decided to do now is sort of forego that process of we're 3D printing all of our sockets, where we can sort of ensure that the design allows for good haptic information or haptic display. But in any case, this video I'll show you really quickly. What you'll see here is sort of the actuation scheme that I was just describing. And then you'll see it being used in what's a standard sort of what we call our box and blocks task. Now, I paused the video right here because I wanted to show you what is the benefit of the impedance control scheme. And to show you that, I'm going to actually ask you to pay attention here to the little ridge. Because what's going to happen is the participant is going to put the block in and move their hand over the ridge and actually make contact with the ridge. But because the hand is in a low impedance mode, you'll see the fingers sort of naturally flow over the ridge, right? As you'll see here. Which is something that would never actually happen with your standard bionic hand because they're always in sort of a high impedance mode. If you hit the ridge, you would basically drag the entire box and blocks task with you. And so this is sort of anecdotal evidence now that there is something beneficial about being able to in real time modulate your impedance while you're performing a task. Okay, I'm gonna start to move a little bit faster through some of this other work to get to the end. The work that I'm showing you in the robotic minimally invasive surgery space is some work done by my current PhD student, Sergio Machaca. This is sort of a kind of illustration of the Da Vinci, which is the standard telesurgical robot that's sort of used in most hospitals for general surgery procedures. It has great vision, stereoscopic vision, great range of motion, but actually no haptic feedback. And so one of the things that we've been focusing in on in my lab is sort of kind of understanding that the clinical device doesn't have haptic feedback. What is the benefit of using haptic feedback in training? And what does that mean for skill acquisition? Because skill acquisition for these robots is actually really difficult because you don't have this haptic information. In fact, what we're starting to sort of believe in the lab right now is that when you look at an expert surgeon that uses this robotic platform, the reason that they're able to be successful in most of the surgeries that they do is because over time, just using this device, they develop what we call visual haptic acuity, right? Which is the ability to look in the visual scene and sort of recognize things that you would normally feel, right? An obvious example is if you touch tissue, right? The tissue starts to blanch, right? The same way my fingernail starts to blanch as I apply pressure to it, right? Blood flows away and you can use those visual cues to sort of get an estimate of your interactions. Unfortunately for novice surgeons, this is a skill that has to be developed, and we're interested in kind of sort of, can we help with this development? So this is work that I started as a postdoc at Penn, where we said, okay, well, can we now just like measure information in the surgical environment and then map it in some, sort of referred haptic way? And what you're seeing here and what you hear is a little wrist-worn device that you can think of like a wrist strap that we put the task on top of a force plate. And so the harder you press on it, the tighter we squeeze your wrist, right? So we get this mapping between force applied and force that we can, sort of sense, even though you can't sense it on the controllers. We sort of have decided to do it in this referred sense because doing direct force feedback on a Da Vinci is sort of complicated. There are a lot of reasons technically why it's not actually done clinically. And so we want to say, let's look at it in a referred sense. This is sort of how it operates in a real task. And we have participants wear two of them. And we can bimanually sort of measure the force of each tool and give back haptic information to each side. So you have an idea of how much force you're actually producing with each of your instruments. So we ran a study saying, how does this, if we give participants this haptic information and ask them to do the task, how does this compare to a group that doesn't have the haptic information? In particular, what we were looking at is what's called the speed accuracy trade-off, because typically it's the case that if I give you haptic information, you might be more accurate at the task, but oftentimes that accuracy comes at the cost of having to slow down and do the task a lot slower. And so we wanted to know, does the speed accuracy trade-off differ for these two groups? What we found overall is that the group that got haptic feedback, which is this red bar that you see at the bottom, produced lower forces. In this case, we had a task that was 12 trials. Each of these trials was moving the ring along the track. Took them about 30 seconds to do it each time. Over the course of those 12 trials, they always produce lower forces. And that was the goal of this task. You don't want to drag the ring along the track. You actually want the ring to basically sit and not make contact with the track at all. And by giving the haptic information, we saw that behavior. So now the question is, okay, they're doing better in terms of the force that they produce. What happens in terms of the speed that it takes them to do the task? And as we sort of expected, they started off very slow, right? Much slower than the group that didn't have this haptic information. But what was interesting is that over time, just doing the task over and over and over again, they got faster, and they actually got faster at a significantly faster rate than the group that had no haptic feedback. And when you look at sort of their last, let's say 2 to 3 trials, what we find is that there's actually no difference between the speed of the group that has the haptic information and the group that doesn't have the haptic information. But the difference is, if you go back to the original slide I showed, the group that has the haptic information is getting faster and producing the same low level of force the entire time. So there's some added benefit now of this haptic feedback in terms of producing behaviors in surgical training that are desirable in terms of like how one would want to operate on tissue. The question that we sort of trying to answer now is, what happens when I turn the haptic information off and you have to go operate in a real surgical environment without the haptic information? What we think is that, and what we hypothesize, and hopefully what we're pitching in grants, is that if you do it enough with the haptic information over time, even when you turn it off, you still learn something. Getting the haptic information helps you pay attention to certain things in the visual scene that when you turn the haptic information off now, you can still rely on those visual cues. Okay, I'm gonna move really quickly through the last slide I'll show you is the work we were doing in the fundamental perception space. So the standard teleoperator interface has a leader and a follower, and the whole goal of teleoperation is to make the leader and the follower what we call transparent. Right? I don't actually realize that there's a robot sort of between me and this glass of water, or this cup of water. That's the overarching goal. The reality, though, is that not only is the robot present, but anytime you put a closed loop controller on that robot, you actually introduce dynamics. Anytime you close a PD controller, right, what you're actually introducing is virtual stiffness and virtual damping. And so, you know, the idea of transparency is more of a theoretical pursuit than it is a practical sort of realizable thing. And so my student and I started to ask, well, what are the perceptual consequences of that? And so what we put together is this, what we call our teleoperator test bed. And let me sort of explain what it is. It's a single degree of freedom teleoperator. And I use teleoperator loosely here because technically the input is here, the output is here. So you're not really operating in a remote environment by any means. But for the same input and output, what we change is the transmission between those two. And I'll show you what they actually are in the next slide. So through a series of capstan drives, we can connect a rigid rod here, which sort of reflects that original Gertz-style teleoperator that I showed you before. We can actually connect the two via 2 electromechanical transmissions, so 2 DC motors, which most telerobotic systems have. And we said, for the sake of it, let's actually introduce physical damping and physical stiffness in there and see what happens. And so these top two are actually a rotary damper and an elastic sort of torsional element in between the two. And we begin to say, what happens now when you actually modulate the dynamics that you feel between input and output, and what effect does that have on your ability to do a task and maybe your ability to perceive the environment? We took the first question first. This is just some work that we did, sort of just validating that, in fact, we do generate different dynamics between the systems, and we have different input-output characteristics for each of these different types of transmissions. And then we sort of ask participants to do this tracking task where we put an object, on the screen, and we use sum of signs to sort of, make the object appear sort of random, and you had to track this task with the teleoperator. And so we sort of kind of came in thinking, oh, well, the Gert style teleoperator, the mechanical one is just going to do the best, right? The only thing you're feeling really is inertia, maybe a little bit of friction in your bearings. But you don't have this added stiffness and dampening, and it's going to do better. What we actually found, and sort of I'm going to illustrate it here, you don't really see any difference in the tracking behavior between each of these. And what you're seeing, each color represents the sort of average behavior for each of the different types of teleoperators. And by and large, they're actually doing about the same thing. They're all tracking the target really well. In fact, when we run the statistics on it, what we found is that there actually are no differences in the tracking errors. So even though we have characteristically different systems in terms of their dynamics, what's actually happening is the operators are compensating for those dynamics. And this is something that was sort of unexpected. And then you can actually see that here. So what we looked at is how much, let's say, lead lag compensation that the operators have to make in order to get the tracking performance to look really well. And that's where we actually found our significant difference. Each teleoperator required a different level of compensation or a compensatory strategy by our operators. And by and large, without any kind of priming or training or anything like that, they were actually able to learn the dynamics of the teleoperator and come up with these compensatory strategies to account for it, to achieve the task, goals, which sort of, we were not expecting that at all. And so now we're beginning to ask the questions, well, what is the limits of this compensatory behavior now? And so we're starting to do more motor control studies with this device now, sort of sweeping ranges of frequency, sweeping different types of sinusoids, changing the parameters of the different systems to say, at what space does compensation just, it can't keep up, right? But this was sort of an interesting result. We also saw, because we had a a force sensor on the grip interface of the device, that basically the impedance, the reflected impedance of the teleoperator, we can sort of see in terms of the grip force that participants had to use in order to actually control it. And this is sort of goes back to some work that a colleague of mine, Bo Yu, did while he was a grad student here, where we actually can measure grip force, and we can see that the impedance differs. Okay. I think this is my last slide, and I'm probably right over time. So with that, I will stop and take whatever questions you all have.
So you defined cognitive efficiency.
Mm-hmm.
And if I understand correctly, this has to do with the ratio between the amount of energy expended on a task versus the amount of cognitive energy versus the amount of physical energy expended on a task.
Sort of. So it's we describe this term neural efficiency as the sort of the physical energy in this case is actually just task performance. How accurate or how well did you do the task according to the metrics that we prescribe, right? Whatever task success looks like, how accurate or how well did you do the task? Yeah, and then the cognitive effort was actually the one that we measure with the FNIR system to look at, sort of the change in oxygenated hemoglobin in the prefrontal cortex.
Okay, right. So what does it mean for the efficiency to be negative?
So yeah, so actually, negative, positive in this sense don't actually really matter. This is actually an old figure that in the paper that we submitted, you actually just take the absolute value of it. It really, negative doesn't matter in this context, in the sense of like a negative efficiency, like one would actually think about. It's just based on the signs and when you do the computation. Yeah. So you could think of it as that actually just being flipped on the positive axis, and it would mean the exact same thing.
Okay. Thank you.
Hmm?
Yeah, so I'm interested about the thing when you say the visual haptic clue signal.
Yep.
Why do you have this kind of belief or hypothesis that the haptic feedback we learn can also transfer to the visual, we can use visual just by vision?
Yeah, so there are a couple of studies that talk about sort of the coupling between visual and haptic information. That's one. I've actually got, another experiment that I didn't even have a chance to talk about, where we actually disrupt or create conflicts between haptic and visual information. And, we sort of see what happens in that space. The other one is sort of anecdotally in my conversations talking to surgeons, right? And so, and also the work that we've done with amputees. So when I talk to surgeons, sort of like, hey, we need to add haptic feedback to the robot, the first thing that they often say to me is, I don't need haptic feedback, I can feel with my eyes. And so, watching them sit at the console and actually perform, there was a surgeon who came in who was a urologist who'd done probably something close to like 3,000 radical prostatectomies, all robotically. He sat down at the console and he started to do these like center out reaching tasks on this robot. And now the robot that we were using was the Gen 1 Da Vinci that he'd sort of operated on, when he first came. This was at Penn. When he first came to Penn, by that time they were already on Gen 3. And he sat there, he was doing these tasks for a while. And after a while, he took his head out of the console. He looked at me, he said, man, this robot has gotten really stiff since the last time I operated on it. And what I realized he was saying was that he was moving his hand to a certain position, right? Perceptively, he sort of knew where his hand was. Visually, he saw that the robot was actually not matching that. And what he sort of quoted and called stiffness was actually this disconnect between where he knew he should be physically in space and where he was. And the reason we know this to be the case is because that robot eventually, the arm that he was operating with died because the potentiometer was actually going bad. The Da Vinci's at that time had dual potentiometers and a digital encoder, quadrature encoder, and a rotary pot. And over time, the rotary pots, just as all rotary pots do, the wipers sort of wipe, sort of mechanically wear, and the arm stopped working because the pot, sort of wore out. So he was actually able to predict before the system actually knew it, that it was actually sort of getting out of sync because he knew where he wanted to go and he could measure where he actually was, right? So vision is actually pretty rich in that regard. In the prosthesis sense, if you ask an amputee to pick up this bottle of water, right, what they're going to do is actually pick it up and watch it deform. And only once they see it deform, right, do they know that they actually have a pretty stable grasp, right? So this is another example of vision actually substituting. If I couldn't feel this grip force, I could still sort of, you could even watch me, right? Sort of pick this up and say, I can keep asking, is it safe? Is it safe? Is it safe? And then you can tell me it's going to work. If you've ever even played the little claw game, right, it comes down and grabs objects in the arcade, right? You're actually using visual information to sort of figure out what is the stable, where can I make a stable grasp in order to pick that information up. There's a whole field of like intuitive physics. I've got a colleague, Jason Fisher, who's at Hopkins with me, that actually does a lot of his studies involve watching, having participants watch visual scenes and make interpretations about physically what's going to happen in the environment without having to physically touch it. So vision is actually very rich. And we've got these sort of intuitive physics engines that are running all the time that help us make estimations. Like, for example, because my bottle is clear, right? About how much this bottle weighs. So when you go to pick it up, you already have an estimation in the motor control plan that's appropriate for this bottle and maybe not this bottle of fluid that you actually have no idea how much fluid is actually inside of it, right? Does that answer the question?
Yeah.
Okay.
In the first part of your talk, you kind of you showed a plot comparing the performance for like the vibration haptic feedback and the joint torque one. You said they kind of violate your hypothesis that maybe it'd be easier to use one versus the other. Is there any difference in the amount of time it takes to learn how to use this specific type of haptic?
Yeah, so in this case, both of these feedback modalities were sort of, I should say, we didn't find sort of a learning curve in this case. In most of the studies that we run, we have this acclimation period where we have participants sit down, we give them the stimulus, like, maybe I'll go grip something, I'll touch the force sensor and they'll feel it buzz, or I'll touch the force sensor and they'll feel the torque on the arm. And very quickly, right, they sort of pick up, oh, this is what it means. You can sort of think about this in your daily experience, right? Like, we have these in our pocket all the time, and every time it buzzes, right, I've learned a mapping now that like a certain buzz means somebody's texting me, a certain buzz means social media is bothering me, another buzz means somebody's calling me, right? I don't have to look at it, but I kind of know, oh, this is my Ring device telling me somebody's at my front door, right? It's just our ability to kind of learn these intuitive, or maybe in some cases non-intuitive mappings, store them in memory such that when we get the stimulus, we sort of pull it back up from memory. Oh, that means this, right? The same way we sort of learn anything like, alphanumeric characters, right? Every time you see the letter A, you know it's a letter A, and you know how to string the letter A with a bunch of other letters together to build words, right? And the same thing sort of happens, I think, in the tactile space as well.
Piggybacking off of that, is there a difference between the actually knowing it consciously versus learning that subconscious? I don't need to think about the fact that I got 2 buzzes, so I know it was a text message, and how that plays into performance.
So that's actually sort of why we think when you look at the cognitive effort measures that we have in those experiments, we're not getting close to the natural limb yet, right? So the natural limb just intuitively works, right? I pick an object up, I feel its weight. I don't have to think, oh, I feel a buzz. This buzz means it weighs about this much, right? Unfortunately, most of our studies in the space are not longitudinal enough to actually see, like, over time, do you actually learn this mapping? I think we do. I think if you sort of got up every single day, right? I mean, and a good example is prism glasses, right? If they've shown studies when you give people prism glasses, that basically, if anybody doesn't know, these prism glasses flip the world upside down, right? And they'll put these glasses on, and for the first, like, half an hour to an hour, people are just sick because the world is all upside down, and what you think is up now means down. But over time, they learn. Right. And by, let's say, by the end of the day, they're operating normally like anybody would, even though visually what they're seeing is the inverse of what they would naturally see. And so I think, our brains are plastic, and I think there is room to always learn. And so I think with enough time and practice, some of these things could maybe start to asymptotically approach what we see with the natural limb. Maybe, the steepness of that curve sort of depends on the intuitiveness of the feedback. And I think that's why approaches that, like Brent's doing with, RPNIs and peripheral nerve interfaces, where you're actually stimulating the nerves, may actually get us to that asymptote a little bit faster than things that sort of buzz and push on your body in unique ways. But I think it is possible.
My other part of that was going to be like the complexity of a signal that you could actually interpret with the different types of sensors.
Mm-hmm. Yeah, and I think we sort of have got there's an open question of, when you look at the hand and what the hand, how many sensors are actually embedded in the hand, what we're doing with a vibrating actuator, pales in comparison, right? We are orders and orders and orders and orders and orders of magnitude off, right? In terms of the number of receptors that you have in the hand, and, sort of the single buzz that we give, sort of a gross global, oh, this is about how hard you're squeezing it. And so an open question is, can we even get to the point where we have as many signals sort of stimulating as we've got sensors sort of receiving? And I honestly am not 100% sure, kind of what the answer to that is.
All right. I mean, I think we're about out of time.
Yeah, I can hang around. I'll definitely hang around for more questions if anybody wants to, has questions that didn't get a chance to ask.
Yeah, thanks very much for coming.